This video will run through the electrophilic addition mechanism with an alkene and bromine. So why does an alkene react, and what kind of things does it react with? Well, the reason that the alkene reacts is clearly the carbon-carbon double bond, and this is a region of high electron density. We know that there are 4 electrons concentrated between those carbons. So who would be interested in electron density? Well, that's going to be something which is short of electrons, and these are our electrophiles. And in this first example we're going to look at bromine. Now, you're quite right in saying that bromine shouldn't really be an electrophile. It's a non-polar molecule, so neither of these bromines is short of electrons. But as the bromine molecule starts to approach a carbon-carbon double bond, then the electron density in the bromine, which is evenly spread out, so if we illustrate the electron density like that, as it approaches the double bond, then those electrons will be repelled away, and the electron distribution in the bromine molecule will be a little bit more like that. So the carbon-carbon double bond is able to polarize the bromine molecule, and this now means that the bromine molecule acquires these partial charges, so the bromine nearest the carbon-carbon double bond becomes electropositive, and the one away from the carbon-carbon double bond is delta minus, so electronegative. So let's have a look when these two things combine. So on the left hand side I've shown the electrons involved, on the right hand side how we're going to illustrate this using curly arrows in a mechanism. So we said that as the bromine approached the carbon-carbon double bond, then it polarized the bromine molecule like so. Now the carbon-carbon double bond, the area of high electron density, is interested in the bromine molecule because the bromine is short of electrons, and what's able to happen is that that double bond can break and those electrons go from the carbon-carbon double bond and make a bond between one of the carbons, doesn't matter which one, could be that carbon, could be that carbon, and make a bond with the bromine. I'll illustrate this with a curly arrow. So the curly arrow starts in the centre of one of the bonds, and those electrons are ending up between the carbon and the bromine. So you'll sometimes see those drawn a little bit closer to the bromine like so. Now as soon as that's happened, that bromine, which only really wants to be bonded to one other thing, and remember those electrons were spending more of their time towards this bromine, so the bond between those two bromines will break and the electrons end up on the lower bromine. Using a curly arrow, so from the bromine-bromine bond to the lower bromine. We now need to show the result of those two curly arrows. Well, as we can see, the double bond between the carbons has broken and we now just have a single bond like so. Instead we have a bond between the carbon and the bromine like so. The other bromine has gained an electron and is now negatively charged, and the other carbon in the double bond lost an electron and now that is positively charged. So we have a positively charged carbon, a negatively charged bromine. So the final thing that's going to happen is that the bromine will be able to give its spare electron and form a bond with that positively charged carbon. So this movement of the electrons, using a curly arrow, So from the lone pair towards that positively charged carbon. And so our final product is the dibrominated alkane. Let's run through this mechanism with one from the notes. So this is the one with propene and chlorine. So there's our propene, and we'll draw our chlorine molecule like so. We can put the partial charges on. So the chlorine nearest the double bond will be electropositive, and this will receive a pair of electrons from the carbon-carbon double bond, and at the same time the chlorine-chlorine bond will break. So what will this make? So there's our propene molecule. We can see that the double bond has now broken. One of those carbons is now bonded to the chlorine. The other chlorine is now negatively charged, and the carbon is positively charged. We need to show the lone pair on the chloride ion, and then the final stage of the mechanism shows the chloride ion forming a bond with the positively charged carbon. And so there is our final product, 1,2-dichloropropane.